So let's talk about Monte Carlo estimation for unknown parameters first. So what exactly is a parameter and what is the estimator for the parameter? We have briefly touched on this in last week's lecture when we talked about Monte Carlo integrations, but let's just recap this. So let theta denote a population parameter that describes some characteristics of the distribution X. So for example, theta can be the location and scale parameters of your distribution X. So something like the theoretical mean or the theoretical variance. Theta can also be the expectation of some function of X, so E of Gx. Let's further go back to the data world. So theta is in the theory world about the population. So in the data world, let's suppose that we draw random samples, x1, x2, all the way up to xn, so a size n sample from the distribution X. Then an estimator of theta, which we denote by theta hat, is actually a function of our random samples. So this is a function applied to our x1, x2, all the way up to xn. It is a function of the samples, so theta hat is a statistic. It's an estimator, it is a statistic, and it itself is also a random variable. The distribution of theta hat, our statistic or our estimator of theta, is known as the sampling distribution of theta hat. So how can we use Monte Carlo approximation for the sampling distribution? So suppose we can draw samples of X, then we can also draw samples of theta hat, which is a function of the axis. So suppose that we can draw theta hat repeatedly and obtain theta hat 1, theta hat 2, all the way up to theta hat m, where each of these m draws for theta hat, so let's say the jth draw, theta hat j, is given by the theta hat function applied to the jth random sample of size n. So x1 of j, x2 of j, all the way up to xn of j. We know how to draw this because we know how to apply the transformation method. We know that by definition that theta hat is equal to the function applied to our random samples. So by the transformation method, we know that we can first draw our random samples, and then by applying the function to them, we'll be able to get the random draws of theta hats. Then the distribution of theta hat 1, theta hat 2, all the way up to theta hat m, if m is large, will approximate the distribution of theta hat. In other words, the sampling distribution that we are interested in. So let's see a few examples of how we can use the theta hat draws to help us with estimation related tasks. Our first example concerns estimation of expectations. So if the parameter of interest, our theta, is the mean or the expectation of a function of x, in other words, theta is equal to the expectation of some function g of x, then we may use the sample mean of our theta hat j draws to estimate the expectation of gx. Well, I hope this brings back some fond memories of week 3 and week 4. So you can see that again, we are dealing with this kind of expectations, and this allows us to apply the Monte Carlo integration techniques that we have learned earlier. So the random sampling and the Monte Carlo techniques will come up to be really good muscles that can help you to work out these tasks that are related to statistical inference. Let's see an example that's more concrete. So suppose that we are interested in the expectation of a function applied to two random samples. So the expectation of the absolute value of x1 minus x2. So this is an example from the textbook. Suppose our x1 and x2 are independent and identically distributed size 2 random samples from the standard normal distribution. This means that x1 follows the standard normal and so does x2, and they are independent. So our parameter of interest is theta, which is equal to the expectation of the absolute value of their differences. In this case, we might take our estimator theta hat to be x1 minus x2, taking the absolute value. Then you can see that if we draw m copies of theta hat, then we can compute the sample mean of the m theta hat draws. So this is given by theta hat bar. So the bar denotes the sample mean. And this is essentially summing all of the theta hat draws up and divided it by m, which is the number of theta hat draws we obtain. You can see that theta hat bar is a unbiased estimator for our unknown parameter theta. So then this gives us a method to use Monte Carlo techniques to estimate the unknown parameter we're interested in. Okay. One more comment about this. So you can see that the theta defined this way, which is equal to the expectation of the distance between x1 and x2. This essentially is a parameter that characterizing the range of our size 2 sample. So if we have an x1 that is standard normal and an x2 that is standard normal, so two independent standard normal random variables, what do we expect their distance to be? Okay, so here are the procedures for implementing the Monte Carlo estimation for theta. To get our theta hat bar, we need to start from generating the theta hats. So for j from 1 to m, m is the number of theta hat draws we will obtain. We first get the random samples of x. So here we sample x1j and x2j, each from normal 0, 1. Then we can get theta hat by transforming the xi's. So here we know that theta hat j is equal to the absolute value of the difference between x1j and x2j. Now that we have our theta hat j's, we have m of them, we can compute the sample mean of our theta hat samples. So the theta hat bar is simply the sample mean of the m theta hat j draws. And then you're done. So let's try to implement this in R. So if you go to Moodle and download the code for examples week5.r markdown, it contains the code for implementing this. And as a side note, there is no participation task for this week. So here's the code. The code is actually quite short. So you have seen that when I explain the procedures, I use some kind of for loop structure, where for j from 1 to m, we implement these things. But we know that for loops can be quite slow in R. So instead of using for loops, let's try to use vectorized operations to replace the for loops. Let's choose m, which is equal to 100,000. So a sufficiently large m will allow us to better approximate the sampling distribution of the absolute value between x1 and x2. So we first draw the x1 and x2s, which are both standard normal samples of size m. And then we can calculate our theta hat, which is the theta hat function applied to x1 and x2. This is given by the absolute value of the difference between each of the entries of the x1 and x2 vectors. And lastly, since we have the theta hat draws of size m, we can compute the sample mean, which is theta hat bar. So I call it theta bar here, so it's a shorter name. This is just the mean of the theta hat vector of length m. And we can see that in this case, the expectation of the absolute value difference between two standard normal draws is given by something around 1.13. So we can also compute the standard error of our Monte Carlo estimators for the expectation. In other words, we can get the SE of theta hat bar, which is our estimate, the Monte Carlo estimator of the expectation. Some students ask me what is the difference between standard deviation and standard error. Well, my understanding is that standard error is essentially the standard deviation of statistics. So if you have a statistic, something like x bar or theta hat bar, then its standard deviation is called standard error. So since the Monte Carlo estimate is a sample mean over m draws, now we know that the standard error estimate can be given by SE of theta hat bar, which is equal to sigma hat of theta hat divided by square root of m. So here the numerator theta hat of sigma hat of beta hat is the standard deviation estimate of our theta hats. So sigma of theta hat is the theoretical standard deviation, and sigma hat is our estimate for it obtained from samples. So how can we get the standard deviation of theta hat, or an estimate of it? Well, since we have obtained a total of 100,000 theta hat draws, well, a standard deviation estimate of theta hat, not theta hat bar, can be obtained by computing the standard deviation of the draws. So that's just given by SD of theta hat, where theta hat is our 100,000 draws. So here's the code for it. So SE of theta hat bar, which is the standard error of our estimator, is given by the SD of theta hat divided by the square root of m. And we can see that in this case, there is a standard error of our MC estimator around 0.003. So what does this tell us? It tells us the amount of random fluctuations we will see in our Monte Carlo estimate of size 100,000. So this time we got that the theta hat bar that was estimated was about 1.1319. The SE tells us that on average, we will expect there to be a fluctuation in the estimates of size around 0.003. So in addition to calculating the mean of the sampling distribution, so that's the expectation of x1 minus x2, absolute value, we can also estimate other sorts of things, such as what is the distribution of this absolute value. So in other words, if we have two standard normal independent random variables, what is going to be the distribution of their distance? We're going to show how we can get this by using a function called density. So if we do plots of density of theta hat, where theta hat are the draws, so the 100,000 theta hat draws that we have obtained earlier, then we'll be able to get a empirical density of our statistic, our theta hat. So this is like an empirical PDF curve. So we'll talk more about empirical density, so empirical PDF and CDF next week when we finish up the Monte Carlo inference stuff and move on to talk about bootstrapping. Well, note that there's another name for Monte Carlo methods for approximating sampling distributions, and that is known as parametric bootstrap. It's called parametric bootstrap because we know the underlying distribution of our test statistic, or we know the underlying distribution of our x's. You can also have non-parametric bootstrap, where you just have some observed data and you don't know what is the underlying distribution of your x's. Then in this case, you can try to do resampling from the observed data and do non-parametric bootstrap. Okay, so other than approximating the mean and the density curve, we can also estimate various sorts of probabilities, like I've mentioned earlier, that are associated with our statistic theta hat. For example, we might be interested in, given two standard normal random variables, what is the probability that their distance exceeds 1? This is given by the probability at the absolute value of x1 minus x2 is greater than 1. In other words, the probability that theta hat is greater than 1, and this is equal to the expectation of the indicator function applied to theta hat greater than 1. So the indicator function is, it will return you either a 1 or 0. So it's going to be 1 if this is satisfied, so if theta hat is indeed larger than 1, and it's going to return you 0 if this is not satisfied. So the right-hand side, the expectation of the indicator function, can be implemented in R, or it can be approximated using our Monte Carlo draws of theta hat by the mean of the true-false test of theta hat greater than 1. So this is essentially implementing the indicator function. It's going to return true or 1 if this is satisfied, and it's going to return false or 0 otherwise. And we can see that the value we get is 0.48, saying that the probability that the absolute value difference between x1 and x2 exceeds 1 is approximately 0.48.